So we just looked at first order equations or linear equations. We'll look now at equations involving second degree polynomials or quadratic polynomials. Okay, so what are our objects of study? So we're looking at things like y equals ax squared plus bx plus c. So recall that a, b, and c are the coefficients. So they depend on the specific problem. Okay? Now, unlike the previous example where we could just look at a linear equation and do some basic algebra to solve for x, here we're going to have to use more delicate techniques, like the quadratic formula and factoring. So let's recall the quadratic formula. We've already seen this, but I want to present it a second time. So what is this helping us do? Well, this is saying if I want to find the roots of a quadratic, then all I have to do is plug the coefficients into the quadratic formula. It's very efficient. All you have to do is remember the formula and then correctly substitute the coefficients and simplify. I want to make a remark again, which is this plus and minus here. So this says that I'm going to have, in general, two solutions, one corresponding to the plus and one corresponding to the minus. In the special case that this doesn't happen, what goes on? Well, this means that whatever is under that square root sign has to be 0. So b squared minus 4ac equals 0. So this is sometimes called the discriminant. And for us, it's discriminating between the cases of having two roots and having one. So let's look at, so how would we handle quadratic inequalities? Well, this is not too difficult. All we have to remember is that two numbers, a times b, their product is greater than or equal to 0 if and only if either both of them are greater than or equal to 0 or both of them is less than or equal to 0. So for example, minus 2 times minus 5 is greater than 0 because there's two negative signs there. So they cancel each other out. So that would be this case here. So this is like two negative numbers. And this would be two positive numbers. Now this observation can be used to help us solve quadratic inequalities. The idea is to say, take your degree 2 polynomial, factor it as degree 1 times degree 1, and then look at when the first factor is positive or negative and when the second factor is positive or negative, and use that information. So right, this is just a simple observation that similarly that if I want to solve an inequality going the other way, if I want to have something less than or equal to 0, I need one to be positive, one to be negative. So this is one positive, one negative. So the idea is to examine each factor individually. So I try to take my inequality and split it up as a product of two factors. So one remark, we can assume a is equal to 1 by dividing both sides by a. So I change the coefficients on b and c, but the right-hand side doesn't change because it's 0, so 0 divided by a is still 0, and I turn the leading coefficient into 1. So here, let's look at an example. I have x squared minus 6x plus 5 less than or equal to 0. So what I'll do is I'll factor this as two linear pieces, and then look at when they're positive and negative. So I can write this as x minus 5 times x minus 1. Does it make sense? This is just observing that I need the x times x to give me x squared, and I need minus 5 times minus 1 to be 5. So I check this. This is x squared minus x minus 5x plus 5. So x squared minus 6x plus 5 as desired. And then I check. In order to have my inequality hold, I need x minus 5 to be positive and x minus 1 to be negative, or vice versa. So let's look at the two cases. So if x minus 5 is less than or equal to 0, that tells me x needs to be less than or equal to 5. And if x minus 1 is greater than or equal to 0, I need x is greater than or equal to 1. So x needs to be greater than or equal to 1 and less than or equal to 5. So x is in the range 1 less than or equal to x less than or equal to 5. And then I look at the other case, where x minus 5 is greater than or equal to 0, and x minus 1 is less than or equal to 0. Then that tells me x needs to be greater than or equal to 5 and less than or equal to 1. And we ask ourselves, is that possible? Is it possible for x to be greater than or equal to 5, so something like 6, 7, 8, and less than or equal to 1, so like 0, minus 1, so on? No. No number satisfies this. So in this case, it's not possible to have x minus 5 be greater than or equal to 0 and x minus 1 be less than or equal to 0. They're disjoint. They have no intersection. So the only way for this inequality to hold is if one is between x is between 1 and 5. So this is the solution set. So let's review how we did this. We factored the polynomial, and then we observed that if I want the inequality to be less than or equal to 0, then I need one of the factors to be positive, or non-negative rather, and one to be non-positive. So I have the first situation here and the second situation on the right. So one more remark that is a little bit more complicated. We can talk about the rates of change of quadratic functions. That is, how are they growing? Are they growing at a steady rate? Is the rate of their growth increasing? This is the question of calculus. One of the first topics in Calculus 1 is derivatives. And the derivative measures exactly this quantity. We're not going to compute the derivatives of degree 2 polynomials, but we are going to make some observations that may be valuable for you on some of the trickier CLEP questions, which is the following. Quadratic polynomials have a rate of change that is a linear function. So think about what this means. The quadratic function, something like this, has a rate of change. And that rate of change is not constant. It says that the step size here and here is growing like a linear function, the slope of this line. So for example, to show you what I mean, let's say that f of x was a really simple quadratic, x squared. Then f of 0 is 0, f of 1 is 1, f of 2 is 4, and let's say f of 3 is 9. Then what would the rate of change be here? It would be the difference between successive values of this function. So it would be like f of 1 minus f of 0, f of 2 minus f of 1, f of 3 minus f of 2. How much am I changing? So what are the change rates? Well, 1 minus 0 is 1, 4 minus 1 is 3, 9 minus 4 is 5. So this looks an awful lot like, well, a linear function. And that function has slope 2. Calculus will make this precise. But this is all this observation is that even though quadratics are growing very quickly, their rate of change is only a linear polynomial. So the rate of change doesn't grow so fast. So let's look at what I consider to be a really tricky example using this. We're going to show you values of a polynomial at different points. And I want you to help me figure out what another value of the polynomial is. So let's take a look. So suppose I have f of 0 is 0, f of 1 is 2, f of 2 is 8, and f of minus 1 is 2. I want to compute f of 3. Now you might think that this is impossible. I don't give you a formula for f. How can you do this? Well, we can use this property we just discussed, that the rate of change is a linear function. So to help us out, let's start by drawing a picture. So at 0, it's 0. At 1, I have the value 2. And then I blow up quickly. 3, 4, 5, 6, 7, 8. So this is the picture I've given you. Can we figure out what f of 3 is? Basically, we're going to do what's called interpolating. We're going to use the points that have already been given to extrapolate to a new point. So what do I know about this function? Well, its rate of change is a linear function. So let's say that, what are the changes here? The changes are 2 minus 0, so 2. And then 8 minus 2, so 6. And then we need one more point. What's the rate of change of 0 to 2? Minus 2. So I have a line whose values at minus 1, 1, and 1, respectively, are minus 2, 6, or 2 and 6. So what's the slope of this line? The slope of this line is 4. Okay? So what this tells me is that f of 3 minus f of 2 is going to be whatever 6 is plus 4. So that's equal to 10. So this is the most tricky mathematical part. I've computed the rates of change at 3 different points and seen that I have a line with slope 4. How does that help me? Well, now I can say, therefore, the rate of change for the point I want to know is the one before that plus the slope of that line, plus 4. So the rate of change between f of 3 and f of 2 is 10. And then I solve for f of 3. So f of 3 is f of 2 plus 10, and I know f of 2. Is 8. So 18. So this is, I think, a very nice mathematical argument. And in fact, I'm going to tell you now what the original function was. The fact is, f of x was 2 times x squared. Does it fit? Sure. At 0, it's 0. At 1, it's 2. At 2, it's 2 times 4, so 8. And now we check. If I plug in x equals 3, I get 2 times 3 squared. So 2 times 9, so 18. So this idea is not totally crazy. It really did work. Now, again, this is one of the trickier CLEP questions, but it can come up. They may ask you about the characterization of quadratics as having linear rates of growth. But this is all they mean. So if you can understand this example, you should be in good shape for these tricky questions.